Okay, good morning, everyone. Welcome back to another lecture. Today, what I want to do is talk about three very important concepts. Before we get into that, though, I want to make sure you're aware of a couple things. First thing is, I mentioned last time we were together that I will give you a quiz, and that's going to happen today. So at the end of this lecture, what I'll have you do is introduce yourself to the class, and I sent you by an announcement some questions. I'll also write them on the board. I'm hoping, I don't know how many people I have connecting by phone. Let me see. Looks like two people, so I don't know. I don't know if you're able to connect or not. I don't know how that works, so we'll have to see. I don't know if you're able to. I think you can use your voice, but maybe not the video. That'll happen today. I also promise you an extra credit assignment. It's a video you'll watch. How big is the universe? That's on Blackboard now, so there's a link, and you want to make sure that you have to take a look at the link and the due date. That's going to count as the quiz grade. So that's one of those extra credit assignments that I mentioned. Quiz 2 is actually posted. Now, we haven't went over the material for Quiz 2 yet, but you might want to take a look at it. You'll see that this lecture should get us into the material to cover Quiz 2. I forget when it's due. I think it might be sometime in the middle of next week. We'll just take a look at it. But Quiz 1 will happen today. Quiz 2, your actual, real, quote-unquote, quiz where you can do calculations, that's posted already on Blackboard. And then there's two documents I want you to look at. One is a periodic table of elements, and the other one is a document called conductors versus insulators. So take a look at that. If I was in class, if we were face-to-face, I would project that on the board and we would talk about it. Since we're doing it this web connection, obviously I can't do that. So you look at it, I'll probably refer to it and talk about it. And what I may end up doing is making a small video that talks about those two documents and how they relate to what we're going to talk about today. So that's kind of the agenda and what's going on. Also, I don't know if you had a chance to print out the topic sheet. If you don't, it's fine. I'll put all the topics on the board, but if you have that sheet in front of you, you can kind of see where we're going with things. But there is one document you'll need. There's a sheet of practice problems, and the practice problems will also help you with the quiz. So if you could print that out, if you have the capability to print, you can print that out. Again, if you can't print it out, I'll write the question on the board, but not the full question. So you have to go back at some point and look at it. So there's some things that you have to look at to kind of go along with what we're going to talk about today. So on the board, I have three terms: voltage, current, and resistance. These three quantities are the only electrical quantities that we're able to measure. Now, there are other quantities we're going to talk about, but we can't measure those directly. These are the most important three. These three quantities we're going to work with for the rest of the semester. And if you take part 2 of the course, you'll work with it for all of that course. And if you have an electrical major, your whole major deals with these three quantities: voltage, current, and resistance. Most people have heard of voltage. If you dealt with a battery, you know battery. One of the ratings on the battery is voltage. Your car battery is 12 volts. If you have a AA battery or you have a C battery, those are 1.5 volts. The square ones, they call transistor batteries. Those are 9 volts. Most people have heard of the term voltage. Probably many people, I won't say most, but many people, they refer to current. They might call it electricity. They might call it juice. So people kind of are familiar with that. Definitely the unit for current, the amp or ampere, I think people probably are familiar with that. And probably fewer people are familiar with resistance. So what we want to do here today, and I don't know if we'll get done with it today, but the goal of this next section, this is chapter 2 stuff, by the way, is to understand the nature of voltage, current, and resistance. By the end of this conversation, you should know exactly what a voltage is. What do we mean by voltage? How do we create or make a voltage? You should know what current is. What is current? How do I make a current? And resistance, what is resistance and what is resistance good for? So we're going to cover a lot of concepts today and probably into Monday. But you want to make sure you don't lose sight of what we're trying to do. No matter how complicated things get or how much we talk about, really what we're trying to do is understand what is voltage, what is current, and what is resistance. That's our goal. Before I start, does anyone have any questions over anything we talked about last class? Any questions at all? Okay, somebody has texted me. I can't pronounce your name. Guys, if you want to ask a question, go ahead and just open your mic, and you can. I don't know if that person's on the phone, but if you have a question, just open your mic, ask it, because my computer is probably 5 feet away from me, and I can see something pop up, but I can't read it. So if you have a question, are you able to open the mic, or do you have the capability? It's last name Birba. I can't pronounce your name.
Good morning, Professor.
Good morning. You have a question?
Yes, my question is about how to connect, how to get connected with the phone. Last time how to get connected with the phone.
With the phone?
Yes.
Okay. I'm actually not sure about how to connect with the phone. I don't on this end. All I do is I set up a link. I believe what you do is that you call in that number, and then there's a code, an access code that you should see with the number that you enter. Does anyone know the answer to her question? How do you connect to the phone?
Yeah, like if you go on Blackboard, you should be able to see all the informations. It's
Okay.
under the course collaborate. They put the number over there and plus the code, the extension code.
Okay. So take a look at that, and if you have a problem, text me, and then I'll see if I can find some better instructions. But on my end, I don't see what you guys see. I can create the link. They give me a number and a link to send to you, but I don't see the same thing that you see on my Blackboard. So see if you can do that. Now, I believe that if you connect by phone, I think you lose, I don't know what capability you lose. You may lose the ability that, I don't know if you can show yourself on video. I'm not really sure. But try that, and if you can't find the information on Blackboard, send me a text to that number that you guys have for me, and I'll see if I can get some better instructions for you. Is that all right?
Yes, Professor, but I was talking about the phone. You just said that you saw two people connected on the phone. So I'm talking about that, how to let you know that we were in the class today.
Yes. So the way you'll do that, when I say two people connect on the phone, what I see on my screen, if you connect with the link, if you clicked on that link, there's an icon with your name under it, so I can see you. But if you connect to the phone, I can't see your name. All it says is a +2. That +2 means two people called in. I don't know who they are. I can't see it. What you're going to have to do today, though, so that I know that you're in the class, at some point today, I'm going to have you, I'll put the number on the board, the same number I gave you last time. And what the students did, you text your name, text me your student ID number and the course number. So I'll have to do that to take attendance so that they know that you're in the class. That's important because if I don't do that, if you don't show up at least one time in 2 weeks, then basically they kick you out of the class and you lose financial aid. So what I'll do here, I won't do it right now, but before this is over, I'll put the number back up here. You'll send me a text to my, I don't have a cell phone, but to that number, and I'll use that to record you for attendance. Now, I'm not sure if that's what you're referring to, but if not, then maybe kind of hold on for a second, and then we can talk more after class. Is that all right?
Yes.
Okay. So I want to go ahead and get started. We got a lot of material to talk about, and so you guys want to make sure you're taking notes on this. Don't just rely on the video because you'll have to write stuff out, but you might have to write some side notes to yourself. So if you're just watching this on camera and you're not taking notes, you're gonna be overwhelmed. So take a second, get you a pen and paper. You should have a calculator. Anytime you connect one of these videos, Have a calculator right there, pen, paper, all of that handy so you can write stuff down and work stuff out. If you just watch me do it, you won't learn it that way. Anytime we do a problem, you want to write it down and try to solve it. So make sure you have all that stuff handy. So I want to get started now. I hear a little bit of feedback. So what that means is somebody has their mic open. So make sure you use your microphones. If not, it's going to mess the session up. Unfortunately, this program we're using is not perfect, but I mean, it'll do the job for us. All right. So we got a long journey to get into this stuff to understand what it is. And here's the way we're going to start the journey. We're going to talk about something called an atom. And I'm sure you guys are familiar with this. To understand the nature of electricity, we have to first start with the idea of an atom. And I think at some point, most of you, through some science class or at some point, you come in contact with this term. You've heard about atoms, depending on what you study. Some of you might know a lot of, if you studied chemistry or physics, you might have really went into some detail about this concept, this idea of an atom. So what I want to do is talk about atoms kind of in general, and we're going to use that to kind of start our discussion to understand what voltage is, what current is, and what resistance is. Now, when you talk about atoms, I want to start by saying there's two models. In science, we use a model because some things we can't really see, so we make models of them. We make models that represent things that happen in nature that's kind of hard for us to see or describe. So when we talk about atoms, atoms are extremely small. We can't see atoms, we can't touch atoms, but we know that they're there. We know a lot about atoms. We even know relative sizes, and we know a whole bunch about them, but those measurements are taken indirectly. And so when we talk about atoms, there's a lot of different kind of models to represent atoms, but there's two main models we use in science to represent atoms. One is called the Bohr model, or the planetary model. And the other one is called the quantum model. The quantum model. We're going to use this model. This is a simplified model of the atom. It treats the atom as if it were like kind of similar to a solar system. The quantum model is more exact. It's more perfect. It's more the real thing, but this is kind of overkill for us. This is more than we need. So if you have a background in chemistry or physics or some other discipline, we're going to use this. And I'm aware of some of the stuff we're going to kind of fudge over a little bit because this does a lot of fuzzing. I only want to talk about atoms enough for us to understand what voltage, current, and resistance is. So some of the detailed quantum model we don't need. So I want to start by saying that. So we're going to start with the Bohr model of the atom. And by the way, Bohr was a physicist that came up with this planetary model, or he was one of the people that was responsible for it. And so they named this after him. So let's talk about the Bohr model of the atom. Now, one of the documents I put up on Blackboard is a periodic table. If you had a chemistry class, you definitely know what the periodic table is and what it's about. And again, I'll make a video on my screen, and I'll talk about the important parts of the periodic table that you need to know for the class. But you want to understand some basic things about the table. And one of the things you want to know is something called the atomic number. So the atomic number, if you look at the periodic table, and I don't know if you have it out in front of you right now, but if you look at the periodic table, you'll see, first of all, a bunch of symbols, letters. And of course, you know those represent the elements, the basic elements. But the thing I want you to know is that each one of those elements has a number. I think the first one in the upper left-hand corner of the periodic table is a capital H. And that H stands for hydrogen, and it's number 1. And if you go all the way across on the other side, on the right side, there's a HE, a capital H and a lowercase e, and it's number 2. And as you go across each row, you'll see that each element is numbered. Those numbers are important. That number for each of the elements is called the atomic number. Atomic number. And what the atomic number does is it tells you the number of protons in that particular atom. Now, we'll talk about protons and other atomic particles here in just a second. But I'll refer to the atomic number and just understand it's that number at the very top of the cell. If you look at the periodic table, you'll see each group of element, each element is in a cell, and that number at the very top of the cell is the atomic number. Now, if I use the Bohr model of the atom to represent an atom, if I start with the simplest atom in that periodic table, if you look at it, is hydrogen. So I'm going to draw a model of what the hydrogen atom might look like. What we will have is this centerpiece right here, and then we have the electrons. So I have the centerpiece of the hydrogen atom, the nucleus, is a single proton. So that's a proton. And then orbiting the proton is an electron. So I think most people have heard of protons and electrons at some point, but I don't know how much you know about it. So there are 3 what we call subatomic particles. When I talk about something being atomic, I'm talking about on the scale of an atom. If it's atomic, it's on the scale of an atom, but the word sub means below. So subatomic means below the scale of an atom. And a long time ago, and I'm talking, this is before Christ, many moons ago, many years ago, the Greeks came up with this idea of an atom. As a matter of fact, the word atom in Greek is pronounced atom, and it means indivisible. It means you can't cut it or break it. So the Greeks for a long time thought that atoms were these little tiny, really tiny spheres that were solid, and they made up all the matter. They made up everything in the universe. And of course, now we know that's incorrect, but it's pretty amazing that they came up with that when you consider they didn't have computers, they didn't have the math knowledge that we have now, they didn't have the science knowledge that we have, but some kind of way they deduced or they reasoned that there must be these tiny parts called atoms, and these atoms make up everything in the entire universe. What they got wrong was the idea that the atom itself is the smallest particle. And for a long time, up through probably the 1700s and or middle 1800s, people actually thought that atoms were these tiny spheres, and that was the smallest piece of stuff that you could have. But now we know that there's actually particles smaller than the atom, and these are what we mean by subatomic particles, and there's 3 of them. One subatomic particle is called the proton, and so I have the proton drawn here. Now you got to be aware of something, guys, what I'm doing here. I'm drawing something that's 3-dimensional on the 2-dimensional surface. So what I'm drawing as a circle is really a sphere. I have a proton as one subatomic particle, and I have an electron as the other subatomic particle. And the third subatomic particle I'm not showing. The third subatomic particle is called the neutron. And so every atom has neutrons except for hydrogen. Hydrogen in the nucleus is just a proton. But if you move over to helium, you'll see helium has atomic number 2. That means there's 2 protons, and we'll talk about electrons in just a second. But it also has a couple neutrons in there. As you get away and you go across the rows of the periodic table, the atomic number gets bigger and bigger. There's more protons in the nucleus and more neutrons in the nucleus. So I'm not drawing the neutron here in hydrogen because there is no neutron. But we're going to talk about other atoms today where I do have nucleus or nuclei with neutrons, but I'll never draw the neutron. The reason is there's this thing called charge, and I'm trying to represent charge here with this plus sign and this minus sign. There's this one of the fundamental quantities in nature that exists. There's many fundamental quantities in nature, like mass. That's fundamental. Charge is another fundamental quantity. We don't really know what it is, but we know that it exists, and we know there's 2 types of it. And so I show one type as being positive and the other type as being negative. So charge, we'll talk about charge today, but I want to show you here that I'm drawing the proton with that plus sign, trying to indicate to you that it has this thing called charge, and the type of charge it has is positive. And the electron has charge, and the type of charge it has is negative. And I'm drawing it, and I'm not showing the neutron because since a neutron has no charge, neutron, neutral, the word neutron, neutral, it doesn't have charge. And so as we go through our study of electronics, we don't have to talk about the neutron because if it doesn't have charge, well, that means it doesn't have any electrical properties at all, so it doesn't concern us in our studies of what we're going to do this semester. So I draw this now. I draw the hydrogen atom. It consists of one proton, and that's in the middle of the atom, and that's called the nucleus. No neutrons, and it has an electron, one single electron. And I'm going to get rid of this because the electron is not just sitting there like that. The electron is actually orbiting the nucleus. So it's actually moving around in this orbit. And that's why they call this Bohr model of an atom, they call it the planetary model, because this kind of makes you think of the sun and the earth, or some star and a planet. We know the earth orbits the sun. Well, here the electron orbits the proton. So that's one thing to know. The other thing to note is the way that I drew this. Now notice I drew the proton way bigger than the electron. And that's because I'm trying to kind of exaggerate the fact that the proton is more massive than the electron. The proton is more massive than the electron. Matter of fact, the proton is approximately 2,000 times more massive than the electron. Now, you might wonder, well, why is that important? Well, the reason it's important is because what we're trying to do here in this class is we're trying to make electricity, or at least we're trying to understand what electricity is. And ultimately, what you're going to discover, the electric current is nothing more than charge in motion. Electric current is charge in motion. And so I have two types of charges. I have plus charge, I have minus charge. I can take either one of those charges, and if I can figure out a way to make it move along a wire or make it move along some material, then I have what you call a current. But I can move either charge. I can move the positive charge, and I can move the charge. Either one makes up a current. Well, it turns out that in nature, small things are really easier to move than big things. So if this is 2,000 times more massive than that, probably the thing that's going to make up what you call electricity is going to be electrons. And so you're going to discover that all electric current is a flow of electrons, not a flow of protons. The proton is too heavy, it's massive, and in addition to that, the proton is always stuck in the middle of the atom, it's stuck in the nucleus, so it's not really free to move. The electrons, if we do things right, we can force them to move away from the atom and move down the wire and make what you call electricity. And so that is something to know. Now, notice I talked about the plus sign and the minus sign and the fact that they represent charge. There's two types of charge. And as this electron is moving around in a circular orbit, it's actually attracted to the nucleus, but it never falls in. And that force of attraction is caused by the fact, and this is important, that these charges actually attract each other. And we're going to talk about today something called the law of charge. The law of charge. And this will by far be one of the most important things that we talk about today. The law of charge. The law of charge says like charges repel, unlike charges attract. Like charges repel, unlike charges attract. So there's a force of attraction between this electron and that proton because the electron has what we call negative charge and the proton has positive charge. So we'll get more into here in a minute. So that's something to observe. Now, let's talk about kind of just relative sizes. I already mentioned to you that the proton is approximately 2,000 times more massive than the electron. We mentioned that already. Well, this distance here, if I were to make this kind of proportional to the real thing, if I had an actual hydrogen atom and I can hold it in my hand, if I can take the nucleus, that proton of a hydrogen atom, and blow it up to the size of a softball. Now, some of you, if you're not from the States, you might not know what a softball is. You probably know what a baseball is. So a softball is just a couple times bigger than the baseball. But if I can blow the nucleus of a hydrogen atom up to the size of a softball and keep everything proportional, the electron would blow up to the size, the diameter of a dime, a 10-cent piece. And this distance right here, this would be the size of a softball, and this distance would be about 5 miles away from each other. So think about that. Imagine me having a softball or baseball or softball sized sphere in my hand, and then 4 or 5 miles away from it, I have this other sphere that's the size of a dime, the diameter of a 10-cent piece, and it's moving around, actually orbiting that softball sized sphere. And it's orbiting it so fast, it orbits it at the speed of light. We talked about the speed of light in our last class, 186,000 miles per second. And so I have such a tiny thing moving so fast that we can say that the electron is actually everywhere at once. It's moving so fast. And the other thing to think about, if I have this sphere that I'm holding in my hand, the size of a softball, and the closest electron to it, the one that's orbiting it, is 5 miles away, then what that says to you is that atoms are mostly empty space. Atoms are mostly empty space. And so it's pretty interesting and fascinating to look at that. And what's even more interesting is if you were to go look into how they figured this stuff out, it's pretty fascinating. But that's a question of physics. All right, so that's one thing. Now, I want to talk about a couple things here. Notice this electron stays in this orbit, so this dotted line represents the path this electron would take as it moves around. Now, the electron is actually doing two things. The electron is spinning and revolving. It's spinning and revolving. Now, you got to know the difference between the two. It's spinning and revolving. So what's the difference between something spinning and revolving? If something is spinning, that means the axis of rotation is through the object. If something is revolving, that means the axis of rotation is outside of the object. And so you usually say that the Earth spins around its own axis, but revolves around the sun. It's the same thing here. That electron is spinning and revolving. It's revolving around the nucleus and it's spinning around its own axis. So I want to mention that because that's important. I think I mentioned last time we were together that in this class, we're going to study electricity, or we'll study that, but we're going to also talk about magnetism, and the reason is you can't have electricity without magnetism. Basically, you can't have one without the other. If you got electricity, you got magnetism. If you got magnetism, you got electricity. So to really understand electricity, you got to also talk about magnetism, and it's the spin of the electron that creates magnetism. That's one of the things that helps create the magnetism. So that'll be important later on. Now, this path, this dotted line that I'm talking about, that shows one orbit or one path that the electrons can take. But as I add more and more electrons to it, which we'll do here in a few minutes, you'll see that there's other orbits. The orbits get bigger and bigger and bigger, and we'll have information that we can get if I can understand how the electrons build in the atom as we add more electrons to it. So we'll get to that in just a few minutes. I want to talk about something else though that's important. This I want to make sure you're crystal clear on, because everything we're going to do, well, not everything we're going to do. If you really want to understand what we're talking about, remember, we want to understand voltage, current, and resistance, then you got to understand this concept of charge. And I kind of say that with a smirk on my face because I'm telling you we need to understand charge, but to be honest, we don't even know, we as scientists, we don't even know what charge is. We just know that two things. We know charge exists. That's a fundamental quantity in the universe. Charge exists. We know that. And the other thing we know is there's two types of it. We call one positive and we call one negative. That's all we know about charge. But here's what I want you to know about charge. I can use the term charge as both a noun and a verb. So write that down. The term charge. Some words in English can be used as nouns or verbs. So a noun is what? A noun is a person, place, or thing. It's the name of something. And the verb is something you do. It's an action word, is what they probably taught you in grade school. Some words in the English language you can use as a noun or you can use it as a verb. An example would be Google. Google. If I say what's that search engine's name? There's a search engine called Google. The name of the search engine is Google. That's a noun. Person, place, or thing. That's a noun. I can tell you to go Google something and you'll go put something in, you'll type it up, you'll look it up in the search engine. That's an action word. That's a verb. So the term Google can be used as a noun or a verb. Well, so can this word charge. And so it can get confusing if you don't understand how this term is being used. You got to understand how we're using it. So write down this fact that the term charge, whatever it is, we know there's two types of it. Other than that, we don't know exactly. We know there's two types of charge, positive and negative. And we know that the proton possesses what we call positive charge, and the electron possesses what we call negative charge. And we know that we have two charges that are the same. Like charges repel. If I have a plus and try to push them together, they're going to push apart. If I have a minus and try to push them together, they're going to push apart. Like charges repel. Like two magnets. You've all played with magnets. But if I have a plus and a minus, they come together. So that's really all we know about charge. We don't know a lot about it, but you can use this term as a noun or a verb, and you got to know how we're using it when we talk about charge. So, as a noun, the term charge is something a subatomic particle can possess. The proton possesses positive charge, the electron possesses negative charge. So charge can mean something that one of these subatomic particles possesses. The other way to use the term as a verb, which is important, it's kind of how we want to think about it in here most of the time. Charge is something you can also do. You can charge something. You all probably have cell phones, and you can use your cell phone, and you know after a while, if you use your cell phone, it's going to go dead. You got to plug it in. What do you do when you plug it in? You're charging it. That's an action word. If you leave your headlights on your car all night and you try to come out the next day and start your car, it won't start because you discharged the battery. What you got to do, you got to recharge it. Now we're using the term charge as a verb, and most of the time in this class, that's just what we mean. But just be aware it can be used as a noun or a verb, and just from the nature of the discussion, you should be able to determine whether we're talking about a noun or a verb in reference to this word charge. But this is very, very important, this idea of charge. Now, notice this plus charge and minus charge. I have that, and we talked about that already. Electron is negative, proton is positive. And we talked about the fact that the proton is bigger than the electron. But here's the thing. Even though it's about 2,000 times more massive, they have the same exact magnitude of charge. This is way bigger, but it has the same amount of charge as the electron. And so what we say about those two charges is that the charge on the electron and proton, they're equal in magnitude but opposite in sign. So this and this have the same amount of charge, but this has plus charge and this has minus charge. Because of that, there's a force of attraction of the electron towards the proton and vice versa. But this electron is going to go in the circle, or sphere. I shouldn't say a circle. Now think about this. If I draw a imaginary box around this, so I draw an imaginary box around that hydrogen atom. Now I want to show you how we're going to use charge as a verb. You understand now charge as a noun. This possesses positive charge, that's a noun. This possesses negative charge, that's a noun. But how do we use this as a verb? So what I want to do is charge this region in that box right there. How do I charge it? How do I use this word as a verb? Well, to do that, if I look at the total amount of charge inside of that box, the total charge in there is 0. You might say, well, hold on a second. What do you mean it's 0? That's positive. That's negative. Why are you saying there's 0 charge in there? Well, yeah, there's positive charge in there. There's negative charge in there, but the net charge, the total charge is 0 because we said that these charges are equal in magnitude, but they're opposite in sign. So let's just make it up. Let's say this was a +1. We haven't talked about units or +1 what, but just roll with me for a minute. This charge was +1. If they have equal charges, then this one is -1. If you take a +1 and the -1 and you put them together, what do you got? 0. And that's why I say that the net charge in this space right here is 0. The net charge is 0. If there was a way, though, if there was a way for me to reach in here and take this electron out of that box and put the electron over here somewhere else in the universe, now when I look in there, I see a charge of +1. I see a charge of +1. I've actually charged this region inside that box. And how did I do that? I did it by taking away an electron. I didn't take away a proton. You can't do that. The proton is stuck in the nucleus. The nucleus doesn't move. If you did split it and try to take it apart, it blows up. You get this mushroom cloud and everything goes to hell. So we can't really do much with the proton. If I want to charge something, if I want to charge this area, what I got to do is take electrons and put them somewhere else in the universe. And so now I have something called a charged atom or an ion. An ion. So here's the thing. I've been talking for a few minutes now, but here's the important thing of what we just went over. This idea of charge. We know there's 2 types, plus and minus. We know that the charge are equal in magnitude, but opposite in sign. We know that we can use the term charge as a noun and a verb, or a verb. And as a noun, it's something that these things possess. It possesses positive charge, the electron possesses negative charge, or I can use it as a verb. That's the one that's important for us, because when you do something electrically, when you charge your phone, when you charge your car battery, or when you discharge something, what you're doing is you're using this as a verb. And so to understand the nature of electricity, you got to understand what we mean by charge as used as a verb. So, but here's something else that's interesting. If I count the charge, let's count them. I got a plus charge here, and I got a minus charge over there. I still got 2 charges. In physics or science, there's this thing called conservation laws, and you probably heard of one. You probably heard of the conservation of energy. Energy is conserved. Excuse me, energy is conserved. What does that mean to say energy is conserved? What that means is energy cannot be created or destroyed. What we say is energy cannot be created or destroyed. All we can do is change it from one form to another. That's called the conservation of energy principle in science, and it's the fundamental principle of science, the most important one. Well, it turns out, though, most people, or many people, they're familiar with that, but they're not familiar with the fact that energy is not the only thing that's conserved. There are other things in nature that are conserved. Energy is conserved, momentum is conserved, mass is conserved, and guess what? Charge is conserved. So what I'm saying is, if charge is conserved, charge can't be created, it can't be destroyed. All we can do with charged particles is move them around. So if I started with 2, let's say, pieces of charge, if I do something, I still have to end up with 2 pieces of charge. So originally, the electron was right here, and that region in that box was not charged because I got a +1 and I got a -1. I add them together, I got 0 charge in that box. But if I want to charge the region of that box, what I got to do, I got to move that electron. So I'm going to move it and put it somewhere else in the universe. When I look at that, and I count, I still got 2 charges. There's one right there, and there's one somewhere else in the universe. So charge is conserved. Write that down. Charge is conserved. So when I charge an atom with something called an ion, and I can have atoms charged to be negative or charged to be positive. Here I removed an electron, and this ion is a positive ion because in this box I have a positive region of charge. But what if I did this? What if I have an electron here? If there was some kind of way for me to force that hydrogen atom to take another electron, if I can force it to take another electron, now I have 2 minus charges and 1 plus charge, so I have a net charge of -1. So now I've charged this ion not to be positive, but to be negative. If I have equal numbers of electrons and protons, then that particular atom is neutral. If I have more positive charge than negative charge, because I removed some of those electrons, then you've charged that nucleus or the atom to be positive. If I can get the atom to add or to take on an electron, I can cause that atom to be negative, and a charged atom is called an ion. So the point is there's positive ions and there's negative ions. But the ion thing is not that important. That's a chemistry thing. What's important for us is understanding this concept of charge, and that I can use charge as a noun to describe something something has, or a verb to describe something that we do, some kind of action that we do. That's the important thing. I want to say a little bit more about the Bohr model of the atom, and I want to move on to some more details of this charge and some other stuff. So now I'm going to move to a more complicated atom, maybe, I don't know, it could be helium. Or maybe I'll just make up an atom. So basically, I got the nucleus of the atom, and it's positive. Now, I'm just going to draw it without putting the charge in there, and I'm going to draw some electrons around it. So what I have is this orbit. And now I want a bigger or more complicated atom, so I'm going to draw other orbits. So this planetary model idea works really well because you know the planets, they revolve around the sun, and so I don't know what the closest, I forget which one is closest to the sun, but you know you have the planet, and then maybe Earth, and then maybe Mars, and the orbits get bigger as we go out further away from the sun. So with these electron paths is the same way. So I can show the orbits like this. And now what I can do is I can start to put electrons in here. So I'm going to put some electrons here, put a couple in here, put a couple in here, and I'm going to put an electron right here. So now I have an atom that has more than just one electron. This is more complicated. By the way, before I get into this, we already mentioned the atomic number in the periodic table. Now, when I make the video, I'll go over this again. Atomic number tells you the number of protons, not the number of electrons. Some people say that gives you a number. It does not give you the number of electrons. The atomic number gives you the number of protons. If you assume you have a neutral atom, then you can say the atomic number tells you the number of protons and electrons. So, for example, helium has atomic number 2. All you know is that there's 2 protons. That's all you can say for sure. Now, if we assume that I have a neutral atom of helium, that means I have 2 protons and 2 electrons. But there's nothing stopping Mother Nature from taking one of those electrons away. It can't take a proton away. That would change the element to something else. But nature can take away an electron, and I don't have a neutral atom. I have an ion. So in here, what we usually do is we assume that the number of electrons and protons are the same. So you can kind of fudge it and say, all right, the atomic number gives me the number of electrons, but just realize really it doesn't. Strictly speaking, the atomic number tells you the number of protons. And if you make the assumption that the atom that you're starting with is neutral, then you can say the number of protons and electrons are given by the atomic number. So that's kind of an important side note. Now, the other thing I want to say about this is that these paths that I have in this Bohr model of the atom, the distance from the nucleus to these orbits is a fixed distance. And we're getting into some physics. I don't want to go too deep into it. But just know that these electrons are orbiting. They can't orbit just anywhere. They can't like come in here. They're a certain fixed distance away from the nucleus. Each one of these orbits is a certain fixed distance. And if an electron is there, it's got to be in one of those orbits. It can't be anywhere in between. That's impossible. It just doesn't work that way. An electron can actually move from one orbit to another, depending on some physics that I don't want to get into. But what I do want to get into is this outermost orbit or ring. This last orbit on an atom, whichever one is the last orbit, is called valence. Sometimes these are called shells. Shells. These orbits are called shells. So shells, they're called orbits. It might be called energy levels. So depending on whose class or what we pick up, there's different names for these. I mean, we'll just call them orbits or shells. It doesn't really matter. But what does matter is the last orbit or shell. That last one on any atom is important because it's called the valence shell. Valence. The last shell, the outer shell on any atom, or on any atom is called the valence shell, and the electrons in that valence shell are called valence electrons. So that's important. So here, whatever atom this is, I look and I see a bunch of electrons in here, but in that outermost orbit, the valence orbit, there's one electron. There's one electron. And so this, we say that there's one valence electron is the way we would say it. There's one valence electron. Now, you might wonder why that's important. Why is knowing the number of valence electrons important? I want to explain that here in just a second. So that's kind of you probably went over this stuff at some point in other classes, the Bohr model of the atom. So that's kind of a little, I'll say, a review. And this is enough for us to move on and get to what we really want to talk about. This will help us understand the nature of voltage, current, and resistance. So I'll come back to this concept many, many, many times during the next few weeks. So you want to make sure you understand at least what we talked about so far about the Bohr model. Anybody have any questions before I move on to the next topic? Okay. We're going to move on to the next topic on the topic sheet. We'll come back to charge because that's actually pretty important. But this topic I want to come back to. So in the study of electricity, we know that there are three categories of what we call materials. Three categories. Three categories. You can have conductors, you can have insulators. And I'll talk about the third one in just a second. So in the study of electricity, we understand that there are different categories of materials. You can have conductors, you can have insulators. So strictly speaking, a conductor is any material that will allow electricity to flow through it with ease. A conductor is any material that will allow electric current to flow through it with ease. Insulators oppose the flow of current. Insulators do not allow current to flow through them with ease. Well, it turns out that if you have a neutral atom, and you count the number of electrons in the outermost shell. Remember we said the outermost shell is the valence shell? If you have a neutral atom and you count the number of valence electrons, then you can predict which material you have, a conductor or an insulator. Now, I need to say something about there. For you guys that know about the quantum model, I need to say something, but I'll get to that in a second. Let's talk a little bit more about conductors and insulators, though, before we get into the science of this. Most of you know that wire is a conductor, usually copper. In your house, you probably have copper wire. You may have aluminum, but they try not to use aluminum. That can be a little bit dangerous. But definitely copper is probably the most famous conductor. Most people know that metals conduct electricity. So wire is made of metal, and the metal of choice for us is copper. Usually what you do is when you're using a conductor for electrical purpose, usually you don't use a conductor by itself. Usually you use conductors and insulators together. So you might have a wire, like I got an extension cord. Let me see if I can show you the extension cord. This is actually running on a light. I got lights down here, and it's making it flash, but this extension cord that I have right here, if you can see it, there's a couple copper wires in there, but around it I have this vinyl material, or sometimes it's rubber. That's the insulator. So normally in electricity, we use these things together. You hardly ever just see a conductor or an insulator by itself. That wouldn't make sense. We usually use these together. So the conductor allows the current to flow through, and the insulator around the conductor allows me to handle this safely without being electrocuted. So I want to say a little bit about that, because on Blackboard, remember I told you there were some documents on Blackboard? I'll make a video of it, but one of those is called Conductors versus Insulators. Now you want to really look at that, because it's kind of neat. What it is a graph. On one end, they have like, I'll say good conductors. They have good conductors. A good conductor would be a poor insulator. A good conductor by nature is a poor insulator. And over here they have bad conductors, but a bad conductor would be a good insulator, right? And they have this line drawn like that on that diagram I'm referring to. And then they do something interesting. They do this. They break it here, and they put a little squiggly thing here, and they break it here, and they put a little squiggly thing here. And then over here, they have examples of good insulators. Like they might have wood, they might have rubber, they might have glass, but they have them kind of like in here showing you that one is better than the other. The further this way you go, the better insulator you have. The further that way you go, the better conductor you have. So you might here have copper, and then silver, and the further you go that way, you get better conductors. But the point I'm making is this little squiggly. What is that squiggly thing? Well, if you're good with math, you might have seen a graph. They might make a graph like this. So they got a graph. Sometimes on the graph, you'll see that squiggly, the little squiggly thing, like this. And what that means on the graph is that this graph actually there's more to it, but they cut it off. So this graph might be miles and miles and miles high, but there's no information in there that really changes. So what they do to squeeze it down to show it on a piece of paper, they do this to let you know there's more there that they're not showing that they cut away. And that's exactly what this means here. Now the significance of this, and again, I'll make a video of this and talk about this paper because it's important, but they got some 10 to the, I forget the number, 10 to the minus 16th or something over here. And the point of this is that they want to show you there's a huge distance, a huge gulf between insulators and conductors. to make a conductor, insulator, or vice versa is nearly impossible. So there's a huge spread between conductors and insulators. So again, I'll say more about that when I make the video. But as I said before, if you start with a neutral atom, and count the number of valence electrons, then you can determine the type of material. If I have 1 to 3 electrons in the outermost shell, it's going to be a conductor. If I have 5, 6, 7, or 8 electrons in the outermost shell, it's going to be an insulator. Now, let me pause for a second for you people who know the quantum model of the atom. If you had a chemistry class and you studied the quantum model instead of the Bohr model, you know that those shells that I drew the nucleus, and then I drew like a shell that shows how the path the electron takes around the nucleus. Well, you people that understand the quantum model know that we really don't have these little lines that we call shells. It's really more like a band. It's more like a band. So maybe I have that band, and in here, in this shell, there's really something called subshells. I'm going to draw them as circles, but they're not all circles. This is why I don't use the quantum model, because it gets confusing. So you can't even imagine some of what I'm talking about. It's hard to imagine, but the thing about it is that instead of a shell being just a line, there's actually these subshells in there, and then they'll use letters of the alphabet like S, P, D. If you had chemistry, you kind of know what I'm talking about. If you didn't, don't worry, it's not important. I'm only saying this to you guys that understand the quantum model, because you're probably sitting there thinking, well, wait a minute. If I have 8, if I have 1 valence electron, 1 to 3, or 5 to 8, what if I have more than 8? And the answer to that is that I'll rephrase it for you people that understand the quantum model. If an atom has 1 to 3 electrons in its outermost shell or subshell, it's a conductor. If it has 5 to 8 electrons in its outermost shell or subshell, it's an insulator. So that's pretty important, because what this enables us to do is to determine when a material or atom will be a conductor, or which atoms are conductors and which atoms are insulators when put together to make up some kind of material. And that's important because we usually use insulators and conductors together, as I said before. Now, if you notice something, look, I skipped the number 4. 1, 2, 3. I skipped 4 and went 5 to 8. If an element has 4 electrons in the outermost shell, it's called a semiconductor. Now, a semiconductor, and science people hate when you say it this way, it's not a good conductor or a good insulator. It's kind of right in the middle, but you can tweak it to be one or the other when you want to. Semiconductors are responsible for everything, basically everything in modern day society. When you talk about solid state and you talk about computer chips or memory, you're talking about semiconductor stuff. So this actually is very, very, very important, but unfortunately, it's not the subject of this class. If your major is EET, if you're electrical major, and you take our electronics course, then they'll talk about semiconductors. That's the whole course of semiconductors. So just suffice it to say, this is very important, but we won't go into any of this. This is beyond the scope of what we want to talk about. But what you got to be able to do is to tell me if an atom is a conductor, if it's a semiconductor, or an insulator. And the way you do that is by counting the number of valence electrons. If I have 1 to 3 electrons in the outermost shell, that material is a conductor. If I have 4, that material material is a semiconductor, if I have 5 to 8 electrons in the outermost shell, then that material is going to be an insulator. The other important thing that I forgot to mention is this number 8. That's called the magic number. If you had chemistry, you know about shells and they call octets. I can't say the word octets. You know the importance of it, but it turns out, scientists call this the magic number because it turns out that when an atom has 8 electrons in the outermost shell, it's stable. Anytime an atom has an octet, it has 8 electrons in the outermost shell, it's stable. And what does that mean to be stable? Well, it's chemically stable, for one, which means that it doesn't react very well with doesn't combine or react very well with other materials. You can't mix it together, it won't interact very well with other atoms. But for us, what's important is not only is it chemically stable, it's electrically stable. And what does it mean to be electrically stable? Remember, we talked about charging atoms to become positive or negative by removing or adding electrons. If I have an atom that's stable, that is, it has 8 electrons in the outermost shell or subshell, then it's really stable, which means it's going to hold those electrons. If you want to try to take one away, it's going to be really hard for you to do that. These kind of atoms that have 8 electrons in the outermost shell, they make the best insulators. So that's important to know. Okay, well, that sounds all good and dandy, you might be thinking, but how in the heck am I supposed to count the number of valence electrons? How do I know how many valence electrons there are in an atom? And that's what I want to talk about next. I want to talk about something called shell capacity. And by the way, guys, I don't know how far I'll get in this lecture today. So I have quiz 2. I forget the due date. It might be Monday or Wednesday. But if I don't get far enough today, then I might move the due date of the quiz. It's one of those things where you got to upload to Blackboard. So if you don't upload it on the due date, then the link disappears and you get a 0. So we'll see how far I get today. And if we don't know enough for you to do the quiz, depending on when I have it due. If I have it due Wednesday, then we'll definitely be done by Monday. But I'll take a look at the due date, and I may move things around. But I will always let you know by posting an announcement if I move a due date or something. I'll never make it closer. I will always give you more time. So the question is, how do we count the number of valence electrons? And the answer to that is shell capacity. You got to know the shell capacity. So shell capacity. Okay, well, what the heck is shell capacity? Well, let me draw an atom and let's label something here. So here is the nucleus. I'm going to color that in. So there's the nucleus. And then you know, as you go out from the nucleus, you got these orbits or shells. So here's an orbit or shell. Here's an orbit or shell. And here's an orbit or shell. Right? And you know that these are where the electrons actually live as they revolve and spin around the nucleus. Well, let's name these shells. Let's name them so I can refer to it. So I'm going to call this the K shell. This is K. This is L. This is M. If I had another one, this will be N. So these are the standard letters we use to represent the shells. They just took some letters of the alphabet. I don't know why they started with K, but what this enables us to do is to now reference a shell. I can say, hey, look at the L shell, you know to look at that circle. Or hey, look at the N shell, you know to look at the outer circle. Along with that is each letter is assigned a number. So I'll put over here, we got K, L, M, N. K is assigned to number 1. This is assigned to number 2. This is assigned to number 3. And this is assigned to number 4. And the way they did that is they just started, since this is the closest to the nucleus, they just went 1, 2, 3, 4. So we got these shell letters, and each shell letter is assigned a shell number. Well, if you know the shell number, then there's something called the shell capacity. The shell capacity, and I'm going to abbreviate that shell capacity SC like that. And shell capacity is, think of it as like a bucket. Remember I was putting electrons in these shells? It turns out that each shell can only hold a certain number of electrons. It's like a bucket of a certain size. When you fill it up, you got to stop pouring the water and move to a bigger bucket. This is exactly how this works. These shells can only hold a certain number of electrons. And when they're full, if you want to keep adding electrons to the atom, you have to go to the next shell. You got to go to the next bucket. What shell capacity is, it allows us to calculate the maximum number of electrons you can put in any shell. So shell capacity is the maximum number of electrons that can fit in the shell. And the way you do that is by using the shell capacity formula. I'm going to write it on the board. So shell capacity is equal to 2n squared, where that n is the shell number. That's the shell number. So on a quiz, you got to be able to calculate that, the shell capacity. So let's calculate shell capacities for each of these shells using this equation. So what I'm going to do, for the first one, the shell capacity is 2n squared. Well, for the K shell, n is 1. So if I put in a 1, I get 1 squared, which is 1. If I multiply that by 2, then the shell capacity here would be 2. So this is the shell capacity. So in other words, that K shell can only hold 2. If you want to put 3 in there, you got to put it in the next shell. The L shell, let's do that one. I put a 2 in here, 2 in here. 2 squared is 4. 2 times 4 is 8. So this can hold 8 electrons. I put a 3 in there. 3 squared is 9, and 2 times 9 is 18. So this can hold 18 electrons. And the last one, if I put a 4 in there, 4 squared is 16, and 2 times 16 is 32. So this can hold 32. The K shell can hold a maximum of 2 electrons. The L shell can hold a maximum of 8 electrons. M can hold a maximum of 18, and N can hold a maximum of 32. So if you have 2 electrons and you're going to put them in an atom, you would add them to the K shell. You put them right here. If you have 3 electrons, you have to put 2 in the K shell, and that third one has to go to the next one. It will go to the L shell. You fill the smaller shells up first and work your way out. And then what you do when you do that, when you get all the way done, then you can count the number of electrons in the outermost shell, and those will be your valence electrons. And the valence electrons will tell you whether you have a conductor, insulator, or semiconductor. So this is very important that you should be able to do that. So, I don't know if you have the documents on Blackboard, but one of them is a sheet of practice problems. Practice problems, and if you have that sheet, go ahead and take it out. I want to look at this one. The very first practice problem talks about classifying copper. What kind of material is copper? Is copper a conductor? Is copper an insulator? Is copper a semiconductor? What kind of material is copper? Well, I think most of you know the answer to that. You all know copper is metal. it's going to be a conductor. But let's say you didn't know. And let's say on the quiz or homework, let's say on some assignment, I give you some kind of material, and I say, all right, tell me if this is going to be a conductor, semiconductor, or insulator. How would you do that? So let's start with copper, and we'll assume that we don't know what copper is. Well, the first thing to remember, you guys have access to that periodic table. So hopefully you got a 3-ring binder and a 3-hole punch, and hopefully you print out that periodic table and you punch it and put it in there because you'll use it. Now, somebody has a question, go ahead and ask me.
Yes, Professor.
Yep.
About the part of shell capacity. For example, if I have an L2, it will be 8. I don't understand. 2 exponent 2 is 4 and not A. So I don't understand why is A and not 4.
You mean here?
Yes.
Okay, so
The mark is 8, 18, and 32. So I really don't understand.
so you don't know, you're saying you don't understand, do you understand these numbers or not?
No, I don't understand. It's
Okay,
like it's the double. I don't understand why is double and not. For example, if K is 1,
yeah,
1 exponent 2 is 1. So if it's L, 2 exponent 2 is 4, but Y is 8.
yeah. So let's make sure we understand what these are. Do you know what
Yes.
these are? Yeah, so this is the 1. So that's 1, that's 2, that's 3, and that's 4. So that's the shell number. Now the way we got these we use this equation for shell capacity. Let me erase this. So shell capacity is equal to 2n. Oh, that doesn't look like an n. 2. Let's see if I can make a better n. Square, where n is this number right here. This is n. So we put that in there. So if I put a 1 in here, I got 2 times 1 squared. That gives me 2 times 1, which is 2. That's how we got that 2. But if I make it 2, if I go to L, put a 2 in there, then I got 2. 2 squared is 4. That gives me 8. You see what I'm doing?
Yes.
Put 3 in there. I get 3 squared. It gives me 2 times 9. That's 18. And on the last one, we put a 4 in there. 4 squared is 16. That's 2 times 16. That's my 32. So that number n is just the shell number right here. This right here, that's the number for n. Does that make sense now?
Yes.
Okay. So you guys I don't care how you do it. You can either use this equation to generate these numbers, or most people remember 2, 8, 18, 32. I mean, it's not that hard, right? You can remember that. But that's how they come up with these numbers using this equation. And this equation, this stuff comes from quantum physics, which is way beyond what we're doing here. But you gotta either be able to get these numbers using this equation, or have it written down somewhere to do what we're gonna do next. Okay, so that was a good question.
Okay.
Now, is there more? Okay. So, given a element in the periodic table, you got to be able to tell me, is it a conductor, insulator, or semiconductor? I think that's on your quiz too also, if you look at that. Well, how would you do that? Well, the first thing you will do, I'm going to get rid of this. Hopefully you wrote this down. On the practice sheet, this is the first problem on the practice sheet. They say that you have a certain element, copper. So what you would do to start this, you got to know the atomic number, because the atomic number gives you the number of protons. So you can't do any of this if you don't know the atomic number. So you either already have to know the atomic number or you have the periodic table. So if I give you something like copper, the chemical symbol for copper is Cu. So I don't know if you have the periodic table in front of you, but if you look up the atomic number for copper, the atomic number is 29. So if on the quiz or homework I gave you, I say, all right, is this element argon? Is it a conductor, semiconductor, or what is it? The first thing you're going to do is look up the atomic number. Because the atomic number is going to tell you what? It's going to tell you the number of protons. We don't need the number of protons. We need the electrons. But what we're going to do is make an assumption. Anytime I give you a problem like this, you're going to assume we have a neutral atom. If we have a neutral atom, that means the number of protons and the number of electrons are the same. So, I told you copper has an atomic number of 29. That means we can assume a neutral atom is going to be 29 electrons. That's how you get the number of electrons. Well, once I know the number of electrons, then it's easy. All I got to remember is K, the shell capacity for K, it can hold 2. L can hold 8. This can hold 18. And that can hold 32. I got to know these numbers, either by remembering this table or using that equation. Now, after this, how you do it is up to you. What I like to do is represent each of these electrons with a dot. I just put a dot up here. And I group them together in tens so it's easy to count. So I'm just going to do what I usually do. I'm going to show the 29 electrons for copper like this. That's 10. That's 10. That's too many. It's 29. I need to get rid of one. So I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9. So I represent my 29 electrons for copper as dots. And then what I do is I start to assign these electrons to those shells. Remember, you start with the K shell and work your way down. So the way to think about it is these two right here, these two are in the K shell. That's K. And then the next 8, that's L. And then the next 18, this is 10, and this is 9. So the next 18, that's M. That means that electron right there is in the N shell, and that's my last electron. So that means copper, the neutral atom of copper, has one valence electron in the outermost shell. Well, if it's in the outermost shell, it's a valence electron, right? So there's one valence electron in copper, which makes it a conductor. If there had been 4 here, it would be an insulator. If there had been 5, 6, 7, or 8, then this would be, I said that wrong. If there was 4, it's a semiconductor. If it was 5, 6, 7, or 8, then this would be an insulator. This is how you'll determine whether an atom is a conductor, semiconductor, or insulator. Since we're talking about copper, I want to point something else out to you, though. Let me draw this as an atom. Look at this. I'm going to show you something. It's not really in the topic sheet, but this is kind of important. We know that copper has 29 electrons, and we know that it has 1 electron in the valence shell. So let me draw that for you. Let me draw what it might look like using the Bohr model. So using the Bohr model, I can just say I got 20. Now, the nucleus is a positive 29 because I got 29 protons. So I'm just going to do a plus 29. That's the nucleus. And then I got these other electrons, so I got to make my shells here. I'm going to make them like this. So what I want to do now is explain to you why is it we use copper so much? I mean, there's many metals. There's aluminum. Well, it's clear why we don't use gold or silver because they're so expensive. But there's other metals that we can use, but copper seems to be the one that we use most often. I want to show you something here. I'm going to draw these electrons in the orbits, and I want to make them red. So these two right here are in the K shell. So these two are right here. I got 2 electrons here. And the next, I got 8. I go 1, 2, 3, 4, 5, 6, 7, 8. And then the next one, I got 18. So I got 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8. And then this one right here is way over here. I'm going to put it right here. There's that bad electron. Well, in order to make electricity flow, I have to have electrons that are free to move. Now, where do I get electrons? Well, electrons orbit atoms. The problem is the electron is kind of stuck to the nucleus because there's a force of attraction. Like charges repel, unlike charges attract. These negative charges are all attracted towards that positive charge. That's what holds the electrons to the nucleus. So how do I get an electron to move away from it? Well, it turns out that, and this should make sense to you if you play with magnets. You know, you've all played with magnets. You know that magnets have north poles and south poles. If I have a north and a north, I try to push them together, they push apart. If I have a south and a south with a magnet, I try to push them together, they push apart. When I have unlike poles, a north and a south, they come together. Charge is exactly the same way. A plus and a plus charge will repel. A minus and a minus charge will repel. But if I have unlike charges, a plus and a minus, they attract. But you also know from playing with magnets that whether I'm talking about a force of attraction or repulsion, the further they are away, the weaker that force is between them. And that's what I want to point out here. The electrons right here, these two are going to feel the K electrons. They're going to feel the most attraction to the nucleus because they're closer. And these here are going to feel pretty strong attraction because they're closer. But as I move further out, the force that holds these electrons to the nucleus is getting weaker and weaker, just like two magnets far apart. That force of attraction and repulsion is getting weaker and weaker. This one's so far away from the nucleus, it's barely attached to the nucleus. So it doesn't take much energy to knock that off there some kind of way and make it a free electron and turn that into electric current. So copper makes a really, really, really good conductor because that 29th electron is so far away, I can get free electrons real easy if I use a material called copper. That's not true of all materials, but that's another topic. Okay, so is everybody clear? If you look at the practice problems, are you clear on how we did the first practice problem? Are you clear on how we did this? Make sure you're able to do this. If not, go back and watch the video. I think I put one of these on quiz 2. I can't remember, but I think I put one on quiz 2. You should be able to do it by replaying the video and going back and watching this. Any questions so far over anything we talked about? All right. Well, we went through a lot so far. Let me see how we're doing. We'll go for a little while longer, and then I've noticed I tried to download the video. I hope you guys know that if you go to Collaborate, you have access to these videos. You should be able to go on your Blackboard. I think there's a Collaborate link there. and you can click on it and you have access to these videos. Now, normally what I do is I put the video files up on YouTube. That way, you know, you might be out somewhere, you don't want to have to log on to Blackboard. You can go to YouTube and get this anywhere on any device. And these files, because our recordings are so long, the file was so big, I tried to download the one from last class and it was taking forever to download. So I don't know, I'm gonna try to get them up on YouTube, but it takes a long time to download them from Blackboard and a long time to upload them to YouTube. So I don't know how well that's gonna work out, but we'll see. But even if I don't, you always have access to these videos on Blackboard. You should be able to go to your Blackboard and see them, and they'll stay there all semester. But at the end of the semester, they disappear. All right. So now we have some stuff to work with. Remember what we're doing. We're trying to understand voltage, current, and resistance, those electrical terms. So on the topic sheet, if you have it out, we talked about atoms, we talked about categories of materials, we talked about how you determine the category of material. I just showed that example. And now I want to talk about something called electrostatics. Electrostatics. And what is that? Well, what this has to do with charge. So electro has to do with charge, and the static means no motion. No motion. That's important because really what we want is electrodynamics. That's what we want, because electrodynamics means we have charge, and the word dynamic means there's motion. And as I mentioned earlier, when you have charge and you make it move, that actually is what current is. But we're getting to how do we make that happen? But to understand that, we got to understand electrostatics. That should have an S on it. So we're looking at charge that's stationary. It's not moving. There's a lot of concepts here, so we'll go into this. And this is probably, I said a lot today, but this is probably going to be the most important stuff we talk about. So let's go through this, and then we'll see where we go after this. We may have to do another video. We talked a little bit about this already, this idea of charge. So I want to go back to that and give you some things to write down and to think about. So let me talk about this. I've already mentioned that a couple things about charge. First is this concept of charge. We know that charge can be used as a noun or a verb. If it's used as a noun, then we're describing it as being positive or negative. If it's used as a verb, that means you're doing something with it. You're doing something with it. So what are you doing with it? Well, we're going to talk about what you're doing with it in just a second. So we've got a noun or a verb. Let me give you some symbols. In engineering and science, we don't like writing stuff out. We use symbols you got to be something. We use symbols to represent quantities. We also use symbols to represent units. Sometimes we use the same symbol over and over again. So you don't want to get confused. So I'm going to show you the symbol we use to represent charge. When I mean charge, what I'm going to use is a Q. So we use that for charge. And actually, to be a little bit more specific, Q stands for quantity of charge. Q stands for quantity of charge. So we're going to use Q to represent charge. Now remember, Q is a quantity. Anytime you have a quantity, you gotta represent a quantity with two pieces of information. you got to have a number or magnitude, and you got to have a unit. So what's the unit for charge? The unit for charge. So quantity of charge, the unit for charge is called the coulomb. And we use a capital letter C to represent that, the coulomb. Now, how do you know since we're using these letters, some letters represent the quantity we're talking about, and some letters represent the unit. Well, the way I'm going to show something as a unit is by putting a bracket around it. So this is a unit. It'll work the same way for, like, we use the I for current. That's the symbol that represents current I. But the unit for current is the ampere. We use an A for the unit. So I might have 10 amps. Well, to show that, say, a unit and not a quantity, I'll put a bracket around it and I'll emphasize that it's a unit. So the unit for Q is C, the coulomb. Now let me say a little bit more about Q. Sometimes in books, you'll see Q written like this, and sometimes you'll see it written lowercase, and that actually does make a difference. It won't, but it does. The difference between this is this right here represents a single charge. So if I have a single plus charge or a single minus charge, I use a lowercase q. This represents a group of charge. So if I have like a bunch of positive charge, like that, then I use a capital Q. I don't really care what you use. If you see me write it this way or that way, for all practical purposes, for what we're doing, they're the same. But in physics, or strictly speaking, this means a group of charge, and this means what we call a point charge, or a single charge. But you can, for me in my class, you can use either one. So we use Q to represent the quantity of charge, and the coulomb is the unit for charge. So let's talk about the unit, a unit. If you think about an amount, for instance, let me think of an example. If you go buy a carton of eggs, right? And one carton of eggs, one carton, there's usually 12 eggs. What else? I think people who smoke cigarettes, I'm not sure, I don't smoke, but in one pack of cigarettes, I think there are 20 cigarettes. I don't know. I mean, you get the idea here that I got the thing I'm talking about and then the amount it represents. So I'm going to do the same thing here. The unit for charge is the coulomb, but where we get the charge is by counting the number of positive or negative charges, counting the number of electrons, basically. So to get 1 coulomb of charge, 1 coulomb of charge, that's going to happen when you group together 6.25 times 10 to the 18th electrons. So you have 1 coulomb of charge when you have this many electrons. That's very important. So write this down. You'll need that. And so we can use this relationship to convert from charge to electrons or from electrons to charge. So go back to that sheet, a practice sheet. If you have it out, there's another practice problem. I'm looking at problem number 2 on the practice sheet. It says you have a neutral dielectric and it has added to it 12.5 times 10 to the 18th electrons. They want to know how much charge is that? What's Q? So if you have that topic sheet out or the practice sheet out, take a look at that problem. What I want to do is work it. It helps when you have these documents out in front of you, so you can read it and see the verbiage and all of that. So if you have it out, or you can bring it up, take a look at it. Now I'm going to write it out, but I'm not going to write the whole problem out, because I don't have the whole problem written out. So this is problem number 2 on the practice sheet. It says you have a neutral dielectric. Well, what the heck is that? We know what the word neutral is. That means it has the same number of positive and negative charges. But what's a dielectric? Well, what you would do is look that up. You guys don't use a dictionary. You'll probably Google it. You'll look it up, and what you'll discover is a dielectric is nothing more than an insulator. So a dielectric and insulator pretty much are the same thing. So you got this neutral insulator. It has 0 charge on it. Well, it has 0 net charge on it. You're going to add to this neutral insulator, you're going to add to it 12.5 times 10 to the 18th electrons. Now, I'm not writing that out. We're going to get away from writing everything all the way out. Instead of writing out electrons, I'm just going to E there for electrons. So right here, what this gives us is the number of electrons. So you got to have some kind of symbol. You can write this out if you want. I'm going to use a little E for that. So I'm using the E here to represent units, and I'm using the E over here to represent the quantity thing that we're talking about. So I got this many electrons is what they say. And they say, all right, well, if I add 12.5 times 10 to the 18th electrons, how much charge is that equal to? What's Q? How much charge will that give me? And you can use this to get it. So go ahead, if you have a pen or paper, work that out for me. It should be a pretty simple calculation, but I just want to make sure everybody can set the problem up the right way. And there's different ways that you can do it, but I like to set it up using these ratios and cancel units out, and that way you can kind of see where things come from. So basically, we're converting electrons to charge. And so to do that, we're going to start with what we got. We got 12.5 times 10 to the 18th electrons. I'm going to multiply that. Now, when I talked about a ratio, what I meant is you can take this, just like we know that, well, I could write this as a fraction like 6.25 times 10 to the 18th electrons, or I can say 6.25 times 10 to the 18th electrons over 1 coulomb. I can write it this way. Or I can write it this way. In chemistry, they call it a conversion factor. You can say that we know that 1 foot is equal to 12 inches. So you can say that 1 foot is the same as 12 inches, or I can say 12 inches is the same as 1 foot. And that's a conversion factor. A factor is something you multiply by something else. So what I want to do is multiply that by either this or that. But I got to make sure I do it in a way to where I end up canceling out electrons and getting coulombs, because that's what I want. Really over here, what I'm looking for is Q. I want to convert that to Q. I'm going to convert that by Q by multiplying by this, because if I multiply by that, then I can see that my electrons are going to cancel out. So the conversion factor I'm going to use is the top one. 1 coulomb is 6.25 times 10 to the 18th electrons. You don't have to do it this way, but I'm just showing you how I want to work everything out so you can see it. Now, if I had picked this one, if I flip that over, then it wouldn't cancel. This E and the C wouldn't cancel. The C would be on the bottom. So I want to do it in a way to where I have things canceling. And you can see here now easily what's going to cancel. Well, electrons will cancel out. Some up, down, and up will cancel. The 10 to the 18th will cancel. And so all I have is 12.5 divided by 6.25. And so that's going to give me 2 coulombs. So if I have 12.5 times 10 to the 18th electrons, that's equal to 2 coulombs of charge. Now, let me point something out here. Remember, there's 2 types of charge. There's negative charge and there's positive charge. If I want to know how much charge I have, you can just say, oh, you got 2 coulombs. But if you do anything else with that number, you got to know that since I have electrons, that this charge is negative. It could have been positive, and I can show you how it'll be positive here in a second. So you got to know. Well, let me see if I can be clear on this, because this can actually be kind of important. Let's say I'm going to add the 2 coulombs. Let's say this is all I have right there. I didn't put it that they're electrons, so it's negative. Let's say I have 5 coulombs of positive charge, and I'm going to add 2 more coulombs to it. Your answer is going to depend on the type of charge that you add. If you add electrons, if you don't put a negative sign there, you're going to think you have 7 coulombs. Don't, because this is actually negative. So you will actually have 3 coulombs of positive charge. So that negative sign you got to supply. It's not in the calculation, what I'm trying to get across to you. So you got to look and say, hey, well, these are electrons I'm using, then these coulombs are going to be negative. Well, you might be wondering, okay, how do you get positive? How do you get positive charge? How do you get positive coulombs? Let me show you that real quick. It's actually pretty simple. So let's say I got some object. And the net charge on the object is 0. The net charge is 0. So maybe I got a charge in here of let's say plus. I'm going to do plus 10. No, let me do I can do plus 10. No, I'll do 100. So I got a charge of plus 100, which means I have 100 protons, and I got a charge of minus 100, which means I have 100 electrons, right? Well, the net charge on here is 0. You can see if I have 100 positives and 100 negatives, they cancel out. My net charge is 0. Now, how do I charge this? Well, I got to move either the positive charge or the negative charge outside of the region. But remember, the positive charge is the nucleus, and the negative charge is the electron. So the only thing you can really move, you can't move positive charges. You can only move electrons, because the protons are stuck in the middle of the nucleus. You don't have access to those. So if I have 100 electrons, let's say I take 50 of these electrons out, and I put them over here. So my 50 electrons are sitting over there. That means over here now I only have 50 electrons in that region. So I have a net charge of 0 anymore. Now my net charge is positive 50. I've charged that to a positive 50. Notice I didn't move any positive charge. I just took away electrons. Charge has to be conserved, we said earlier. So if I started with a net charge of 0, or if I started with 100 positive and 100 negative, I still got to have that. There's my 100 positive. There's my 50 negative, my 50 electrons, and there's my other 50 over there. Charge has to be conserved. But to charge the object, what did I do? I took electrons and I moved them away from that region. So my Q here is a positive Q, but my Q here is a negative Q if these were coulombs instead of electrons. So that's how you get positive charge, by removing electrons away from something. And if I have more positive charges than negative charges, when I take those electrons away, then I've charged that thing that I've removed the electron from to be positive, and wherever I put the electrons in the universe, that region now is negative. So hopefully that's clear. Now there's another problem on the topic sheet I want to do. Problem number 3. So it's just like this one. So go ahead and do problem number 3. Problem number 3 on the topic sheet. It says this time you have a charge of 3 coulombs. So they tell you Q. They tell you Q is equal to 3 coulombs. And then we'll say, all right, if I got 3 coulombs of charge, how many electrons is this? So here we're looking for the number of electrons. I'm just going to show that with a question mark. Now, notice I don't have a negative sign here because I don't need it. I'm not doing anything with these coulombs. I know they're telling me that they're electrons. These coulombs, these 3 coulombs come from electrons. So I know the sign of this is a -3. But since I'm not combining this with another charge, I can just leave it as 3. I'm not concerned about the sign now. But if I have 3 coulombs of charge, how many electrons is that? Well, again, we use conversion factors. I'm going to start with what I have. I'm looking for the number of electrons. I'm going to start with what I have, 3 coulombs. And I'm going to multiply by a conversion factor set up in a way that I can cancel the C out. So I'm going to multiply this by 1 coulomb. It's the same as 6.25 times 10 to the 18th electrons. If I had done it the other way, then the C and the 10 to the 18th E wouldn't cancel out. So this is the only way to put it in there to make those C's cancel out. And so if I cancel them out, this will cancel with that. And now my units are electrons, what I want. And 3 times 6.25 gives me 18.75 times 10 to the 18th electrons. So I can easily go from the number of electrons to the coulombs and vice versa if I need to do that. So I think on that quiz, I probably asked some about this on quiz 2. When you look at that, that's how you do that. So any questions over any of this so far? All right. Well, couple more things, and I think we're going to cut it off. I'm getting to the point to where we can go for, another couple hours, but that would be unpractical. So I'm not going to go too much longer. We'll see. We may. I don't know. We'll see. All right. So electrostatics, we talked about the coulomb of charge. We use Q to represent charge. The coulomb is the unit of charge. We express the unit as a coulomb or capital C. I've already mentioned the fact that there's 2 types of charge. You know, there's positive charge and there's negative charge. And one very important concept on the topic sheet is the law of charge. I mentioned that earlier in the lecture. The law of charge. That's important. What we're doing now is more physics. When we start with electrical stuff next week, it all starts with the law of charge. So for one more time, the law of charge says like charges attract, unlike charges repel, right? I got it backwards. Like charges repel, unlike charges attract is what you want to remember. I said it backwards on purpose. So, all right. So now I want to talk about, remember we said that you can use charge as a verb? I want to talk about that because what does it mean when you charge something? What can you charge? You can charge your cell phone. You can charge your car battery. You can charge. You have these devices you can charge. You can charge them up. What does that mean? So let's talk about charging. There's a very specific meaning. And here is where I'm using the term charge as a verb. And I've already actually showed you this. I just showed it to you. If I have a region of charge, actually, let's just do one atom. We'll charge one atom. So let's say I have an atom with +4 in the nucleus, and I want to draw 4 electrons the wrong way. So I'm going to put an electron here, 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 and here. Negative, 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 negative. Now it's drawn the wrong way because I know I can only have two. I gotta have two in the K shell, and then I can go out from that. But I'm not trying to emphasize that right now. I'm trying to get you to see though that if this represents an atom, the net charge on that atom is zero because I have 4 positive charges and 4 negative charges. So the net charge is zero. So again, what I'm going to do, this region around this atom, I'm going to put this dotted line. Actually, let me use a square. I don't want you to think that's an orbit. So say I'm looking at this region. I'm going to put this in a box, an imaginary box. What I want to do is charge this region of space. How do I charge this region of space out of the box? The way you do it right now, the net charge is zero. The way I charge it is I got to come in here and I got to remove an electron. Now, it's not going to be easy because remember, unlike charges attract. So there's a force of attraction this way. It's like taking 2 magnets apart and stuck together. You got to put in a little bit of work to do that. So it's not going to be easy, but I can eventually separate this and take this charge and put it over here. And now when I look at this, I've charged this region. I have 4 positive charges with only 3 negative charges. This region now, if I take 4 minus 3, that's a plus 1. Is my charge conserved? Well, yes, it is. So I got 4 protons in there. I got 1, 2, 3 electrons, and the 4th electron is somewhere else in the universe. Remember, you can't create charge, you can't destroy it. Charge is conserved. So I got to be able to account for all my charges. 1, 2, 3 electrons, and there's a 4th one over there on the other side of the universe. But now what I've done by removing that 1 electron, by taking it away from the atom, I've charged this region in space to plus 1. What if I want a higher charge? What do I do? I'll take this electron, put it over here, and now I got 2 negatives and 2 positives. I've charged this thing now to plus 2. And you can see I can keep going with this. So this is a very simple example, but oh boy, is it important. What does it mean to charge an object? What it means to charge an object, your phone, a battery, no matter what, when you charge something, what you're doing is you're moving electrons from one place to another. The specific meaning of charging, when you charge your cell phone, your car battery, or whatever you're charging, anything, that means you're taking electrons and you're moving them from one place to another. So the concept of charge deals with a transfer of electrons. There must be a transfer of electrons for charging to take place. That's what you're charging. And so what I want to do is talk about 3 basic ways to charge an object. We're talking about electrostatics, so we're not talking about charge in motion. I mean, we move the charge and we set it there and it's stationary. It's not moving like an electric current. So charging deals with transferring electrons. That's what you want to understand. And now we're going to talk about a couple ways that I can do that. 3 ways to charge an object. One is friction. 2, by contact. And then the last way is called induction. You can charge an object by friction, contact, and induction. These are 3 ways to move electrons from one place to another, from one region to another, so that I end up with a charged region. So let's talk about each of these and give you an example. Now, most people are familiar with the first one, friction. What friction, basically to get friction, you rub things together, right? So you know that maybe when it's cold outside, people do this, and they rub their hands together to warm them up a little bit. You know that if I take a ball and I roll it down the hallway, eventually it's going to stop even if it doesn't hit anything because friction opposes motion. So if you've ever been in a situation where maybe the air is real dry and you have on gym shoes and you drag your feet across the carpet, then you reach over and touch somebody, you can shock them. Sometimes if you turn the light out, you'll see a little spark. You've done that before where you rub something against something else and you maybe a person, your feet on the carpet and you touch a person, you can shock them. That's charging by friction. If you start off initially neutral and you drag your feet across the carpet, the frictional forces can actually cause electrons to build up, to go from the carpet to you, to build on you. And so the transfer I'm talking about is actually a transfer from the carpet to your gym shoes or to your body because you're rubbing your shoes against the carpet. You can do the same thing with a balloon. Oh, I can't. I don't have any hair. If you've ever taken a balloon and you rub it on your hair, you can stick it on the wall and it'll stick there because there's a transfer. You've charged that electron, you charge that balloon by transferring electrons, and now you're able to, because there's a difference in charge between the balloon and the wall, it's able to stick to the wall. So one way to charge objects is by rubbing something against something else. That doesn't work all the time with all objects, but on some objects it will work. Rubber will work like that, right? If the gym shoes are rubber and you drag them across the carpet, you can reach over and touch some and you'll see a spark. You'll feel a spark. That happens because you transferred electrons from the carpet to your body by rubbing or dragging your feet across the carpet. That's friction. Though you look closely at that example that I just gave, you'll see that really there's two transfers that take place. The first one is when you drag your feet across the carpet, there's a transfer of electrons from the carpet to your body because of the frictional forces between your shoes and the carpet. And then when you reach over and touch somebody, there's a transfer from you to the person that you touch, or maybe you touch a doorknob because of contact. If I have enough electrons on my body, if I reach over and touch something that has fewer electrons, it'll go from me to that. I don't have to rub. There's no friction involved. I can just touch it by contact, and I can zap. I can move from some electrons from my body to some other object. So one way to transfer charge is by friction, rubbing things together. If I have a buildup of charge, I can transfer by contact. If I have more charge on something than on something else, the thing with more charge, when I touch something with less charge, the electrons can go over to that other thing. So I can charge by friction. I can charge by contact. The final way to charge an object is through induction, and that's actually a process. We got to talk about that. That's the process. So let's talk about that, and then we'll see how we're feeling here about the rest of this material. I think what I'll do is probably after this, I'm going to call it quits because we still haven't gotten to the question I want to answer, the nature of voltage, current, and resistance. But we're going to start with voltage, and that can easily, that's going to be a discussion for you to really understand it. So I think this will be a proper time to break. Once I'm done with this, we'll end this and come and refresh, and you'll be ready to hear more about this, because that's going to be, it's important because that's really what I want to talk about. But it's going to take some time to get that way. And since you've been listening to me for hours, I'm sure your mind is starting to wonder now. So we'll stop after I get done with this induction thing. So this induction is a process. I got to draw a picture for you. So just follow me for a second. Suppose you have a metal ball, a metal sphere hanging from the ceiling. So I got this metal ball hanging from the ceiling. And the ball is neutral. So the net charge is 0. Well, if the net charge is 0, that doesn't mean it doesn't have any charge on it. That means it has the same number of plus and minus charge. So let me draw that. Let me draw some plus charge in there. Let me draw some negative charge in there. And you can see I have 1, 2, 3, 4, 5 positive charges and 1, 2, 3, 4, 5 negative charges. So the net charge on the sphere is 0. Now what I want to do is take a glass rod. So I got a glass. This works really well with glass. Rod. So I got this glass rod. And what I can do is take some silk or some material and just rub that rod. And just like electrons were transferred from the carpet to your body from dragging your shoes across the carpet, if I take some like silk and rub it across a rod, I can transfer electrons from the material to the glass rod. I can charge this to be negative. So let's say I charge that to be negative. So here is my glass rod. And I've rubbed something on it and charged it. I put this negative charge. From friction. Right? So once I've charged this to be negative, what I'm going to do is take that glass rod and I'm going to put it over near here, like that. I'm not going to touch it, because if I touch it, there could be a transfer of electrons. I don't want to do any electrons going from here to there. I just want to get near there. When I get near there, what's going to happen, if you think about it, I mentioned that this is a metal sphere. This is metal. That's important. It's metal. And the reason that's important is because, you know, in metal, current, electrons can move in metal. Current can move through a wire. So if I take this glass rod, which I've charged to be negative, and I put over close to here, these electrons are free to move. What's going to happen is, since like charges repel, what's going to happen is the electrons are going to be forced to one end or one side. They're going to be pushed away. They repel. Let me put my rod over here so you can see it. So here is my glass rod, and I've charged it to be negative. So the electrons are going to be pushed away, and the positive charges are going to exist over here. But I still got the same number of negative and positive, so my net charge is still 0. But while you're doing that, while you have that glass rod close to that sphere, somebody else comes over here and they take a wire and they touch from here. Now, I don't know if you know what this symbol is, but we'll talk about that. This symbol right here is important. If you've ever seen that before, that symbol means ground. And I'm talking about ground that I'm standing on. When I do that, what's going to happen is those electrons are going to be transferred, sucked right off to here, because those electrons want to go to ground. That happens as soon as I touch that sphere. And when I take it away, I provided a way for the electrons to get off of the sphere. So now when I move this back, the only thing I have left here is positive charge. So I've charged this now to I think there's 5 there, to a plus 5, if I'm just using these numbers. So that's why I say this idea of, this is induction, charging by induction. That's the process. That's the story. So hopefully you understand that, but the thing to understand is there's 3 ways to charge. Friction, I can charge by contact, and this process of induction is another way of charging, but you see that's a process. I had to go through several steps to get this thing charged to what I wanted, the plus 5. Now, we went through a lot today. We have more to go through. We still haven't gotten to, what we've done now is kind of set the groundwork to answer the question, what is the nature of voltage? What is the nature of current? What is the nature of resistance? We set the groundwork for all of that. We haven't even gotten to what we want to answer yet. But I think this is the proper time to break. I mean, we can probably get through it in another hour, but I think you guys are. I don't think I'll get the attention from you that I'll get if we try to do that fresh and when we're in the morning. So we're going to end this now. I want to just double check the due date on quiz 2, because since I'm not going to finish the lecture today, I'm going to finish it on Monday. I want to make sure that you have enough time to do the quiz. So if it's due Monday, I don't want it to be due Monday. I'll change the date. If it's due Wednesday, you probably can still turn it on Wednesday if it's due on Wednesday, because I think we'll be done. Definitely Monday we'll be done with this stuff, and you should be able to do the calculations. You'll have the rest of Monday, Tuesday, and then Wednesday, and it'll probably be due like Wednesday at midnight or something like that. So I'll check into that. So we're going to end this now. Before I do, does anyone have any questions on anything I talked about? Don't sign off yet, because there's 2 things we got to do. Does anybody have any questions over anything I talked about? Okay, well, here's what I want to do. We still got to do quiz 1. That's what you guys are going to do your introductions. But I wanted to wait till the end, because I want to. I'm going to put this on YouTube probably, and I don't want your guys' name to be. You may not want your name on YouTube. So what I'm going to do is stop the recorder, and then we're going to continue with the class to finish up quiz 1. And I want you to send me your information. Actually, we'll do that first. I'll have you text me for attendance, and then we'll do the quiz. So let me turn the recorder off.